So just like with L'Hopital, sometimes integration by parts has to be used more than once. Here's an example of that. I have x squared e to the x. So like you can sort of think ahead. If I can do the antiderivative of e to the x as many times as I want, it just stays e to the x. Or if this was sine x, it just switches back and forth, cosine, sine, positive and negative. But x squared, every time I take the derivative, it gets smaller until it goes away. So that's why I want to use the x squared as the u and the e to the x as the dv, and I'm going to have to do it more than once. So I'm going to lay out my table, my u, du, my v, and my dv, and we're going to remember that I like to put the x squared for the u and the e to the x dx for the dv, so I'm filling in these two diagonals first. Some people turn this one around. I don't like to do that, but it's up to you. Do the derivative, 2x dx. Don't forget to keep the dx there. Do the antiderivative, e to the x. That's no longer a dx because we did an antiderivative. And then rewrite the formula, rewrite the integral. I have integral x squared e to the x dx, and I'm going to be using integral of u dv is equal to uv minus the integral of v du. So that is x squared e to the x is my uv, minus my integral of v du is e to the x times 2x dx. So I'm going to put the 2x first, e to the x dx. All right, now I've got another integral that I need to use parts again. Now, just because I'm writing underneath like this, I'm going to just bring the whole thing down. I don't mind writing the same thing over and over again. It doesn't bother me at all. Let's see. If it helps me to organize my work, I don't mind doing it. So then what's going to happen is in this one, I need to apply integration by parts again. So I can differentiate the u. I mean, I could pull out the 2 first if you wanted. You could do that. You could pull out the 2 first. I'm not going to do that. And then this is our dv. So in this second application, I'm going to use u equals 2x and my du, and v we'll figure out, and my dv is again going to be e to the x dx. All right, so my du is going to be 2 dx, and my v is going to be e to the x. Now, when I rewrite yet again, because I wrote these things in the middle, so it sort of forces me to do that. You wouldn't have to do that necessarily in your work. X squared e to the x, okay? And then I have to go minus. Now, I have to watch out because that minus is going to distribute, because in here I have to put the new uv minus integral v du. To put the new one in there. All right, so my uv is going to be 2x e to the x. And then I have minus my integral of v du is going to be the integral of e to the x 2 dx. So let's write that as 2 e to the x dx. All right, and so I just put a big bracket so that I can distribute that negative sign. And then I can just work out the rest of it. So I have x squared e to the x minus 2x e to the x. And I'm distributing this minus sign, so I'm going to have plus. And then I'll go ahead and do this antiderivative. It's going to be 2 e to the x plus c. There you go. All right, so that's doing a 2-step L'Hopital. All right, here's another fun thing you can do with L'Hopital's rule. What is the integral of ln of x dx? Now, from your colossal compendium of derivatives, you know what the derivative of ln of x is. It's 1 over x. And so we know that the antiderivative of 1 over x, the antiderivative of 1 over x, is equal to ln of absolute value of x. All right, but you don't know what the integral of ln x is. There's not really an easy way to get that, except by parts. So here's what you do. You think of this as being 1 times ln x, right? Then you let the ln of x dx, well, you let the ln of x be u, and the 1 dx be dv, right? So you're really laying it out like this. U is ln of x, dv is 1 dx, all right? Because you don't mind integrating 1, it's just x. And you love doing a derivative of ln x, it's 1 over x dx. And then look what happens when you write the integral of ln x dx equals, I want uv minus the integral of v du, uv is x ln x, I put the x first because it just flows better, minus the integral of v du. Well, look what happens is x times 1 over x dx. So that equals x ln x minus the integral of 1 dx. And the integral of 1 is just x, so it's x ln x minus x plus c. Ta-da! That's the antiderivative of ln x. Who would have guessed that? That's another thing you can do. So sometimes when you're doing antiderivatives, we'll see another example of this. Sometimes when you're using integration by parts, you don't even necessarily see a product. You just see something that, I know the derivative of this, but not the antiderivative. And what the process allows you to do is exchange your unknown antiderivative for a known derivative, and then let you rewrite the problem and get something that you can work.